Okay, what if I told you that one single AI technique is behind all of it? We're talking creating stunning videos, folding proteins so well it wins a Nobel Prize, and even driving a car. And what if I told you its core logic is just about 10 lines of code? Well, today we're breaking down exactly that technique, diffusion.
So let's just dive right in. This is about a fundamental machine learning framework that has kind of quietly just come to dominate almost every single field of AI. We're talking image generation, robotics, you name it. And the craziest part? The idea behind it is surprisingly simple.
At its heart, you can think of diffusion as a really simple game. A game of noising something up and then denoising it.
That's it. It's really just a two-step dance. Step one, the easy part. You take a piece of data, let's say an image, and you just blast it with random noise, again and again, until it's just static. Then comes the hard part, step two. You train a model to learn how to do the exact reverse trip. That denoising part, that's where all the magic, all the learning actually happens.
So let's just picture this for a second. We start with our goal, right? A clean, perfect, structured piece of data. This is what we want our model to eventually be able to create completely from scratch. Then we start what's called the forward process. And all that really means is we gradually corrupt the data. We just keep adding more and more random noise, systematically destroying that beautiful original structure. And we don't stop until we're left with pure, unstructured static. Total chaos. Now, this might seem weird, but this noisy mess is actually our starting point anytime we want to generate something brand new. And this is where the genius of the whole thing comes in. The model's only job is to learn that path backward. It figures out how to take that pure static and, step by step, carefully remove the noise until, boom, it reconstructs the original clean data. That's the entire concept.
Now, what is absolutely mind-blowing is how this one simple idea has become a universal engine for progress across, well, pretty much the entire field of AI.
I mean, just look at this list. The applications are staggering. DeepMind used this for protein folding with AlphaFold, which led to a Nobel Prize. It's being used for drug discovery. It's literally driving cars with something called diffusion policy. It's the engine behind GenCast, the most accurate weather forecaster in the world. And of course, it's what's powering these incredible video models like Sora and VO. Code, robotics, even finding rare system failures. It's everywhere. So here's the bottom line. Diffusion has basically eaten AI. It's become the dominant approach. The only two major areas where it's not yet the undisputed king of the hill are in those big language models that generate text one word at a time, and in game-playing AIs like AlphaGo. Everywhere else, diffusion is running the show.
Now, you'd probably think that as these models got more and more powerful, they must have gotten way more complicated, right? Well, the exact opposite is true. The whole story of diffusion is a story of radical simplification.
The evolution is it's fascinating. So the original paper back in 2015 had all the key ideas, but the math was super complex. Then researchers had a breakthrough. They realized, hey, instead of making the model predict the previous clean image, what if we just make it predict the noise we added? Turns out that's way easier. Then they realized it's even easier to just predict the velocity, the direction of change. And that simple idea led to the latest and greatest breakthrough, flow matching.
So the old way forced the model to learn this complex, winding step-by-step path from noise back to the data. But the new way, flow matching, just teaches the model the straight line, the direct path. It is a massive leap forward in elegance and efficiency. So what exactly is flow matching? It's this simple. Forget all the intermediate steps. The model learns one and only one thing, a global velocity. You know, imagine you're lost in a foggy forest. The old way was like trying to retrace every single one of your steps backward. Flow matching is like someone just handing you a compass that always points directly home, no matter where you are.
And this is where it all gets, well, kind of unbelievable. This powerful, elegant idea can be implemented in just a handful of lines of code. Let's just walk through exactly how this revolutionary simplicity works.
Okay, first you grab your clean data and some random noise. Then you pick a random point in time, we'll call it t, somewhere between 0 and 1. And then you just mix them. You create a training sample, xt, by literally just mixing the data and the noise together based on that t value.
Now, here it is, the core logic. The target velocity, that straight line path home, is just the noise minus the data.
That's the answer key. So we show our model the noise sample, xt, and we ask it to predict that velocity. The training goal, the loss, is just making the model's prediction as close as possible to the real target velocity. And that's it. That is the entire training loop.
And here's the most powerful part of all. This little piece of code is completely universal. It doesn't care if your data is an image, a protein structure, financial data, a robot's movements, whatever. The flow matching procedure stays exactly the same. You just swap out the underlying model for one that understands your type of data.
Okay, so this incredible simplicity and power, it leads you to a much deeper question. Does this approach tell us anything about the nature of intelligence itself? So, the AI pioneer Yann LeCun has this great idea he calls a squint test. To achieve flight, we didn't need to perfectly copy a bird's flopping wings, but if you kind of squint at an early airplane and a bird, you see a fundamental resemblance. They both have two wings. So the question is, does diffusion pass the squint test for intelligence?
Well, let's compare it to how a large language model works. An LLM thinks one word at a time, in a super strict sequence. It can't go back and revise. Diffusion, though, it starts with a messy, holistic concept and then iteratively refines it, which is a lot more like how we might write a draft of an essay. And maybe most importantly, it uses randomness as a core part of its learning process. It just feels a lot closer to how we humans think and create. So look, this isn't just some philosophical debate. This shift in thinking has really profound, practical implications for anyone out there who's building in this space.
So here's the big summary. If you're someone who trains models, you have to be looking at diffusion for pretty much any application you can dream of. It's that fundamental. And if you're a founder or just a user of this tech, the message is even simpler. Update your expectations. This technology is getting better and simpler at an exponential rate. All those things that seemed impossible in robotics, biology, and creative generation, they are going to work. You need to skate to where the puck is going.
All right, so let's quickly recap what we've covered today. We learned that the core idea of diffusion is incredibly simple. Start with pure noise and train a model to reverse that process back to something structured and useful. We saw how this one simple idea has become the engine behind breakthroughs in almost every corner of AI, from medicine to making movies. And crucially, we saw how the technology is evolving to be radically simple with flow matching, a concept you can code up in just a few lines. So as the core logic of our most powerful AI gets simpler, more elegant, and more accessible to everyone, what new impossibilities are you going to make possible?